You forgot. I forgot that I had an air horn. Now you know. Now we remember. Okay, let's get into it. So we're going to continue down the line with this calculations of cell potentials. But now we're interested in converting these into other types of quantities, such as work. So when we arrange an electrochemical cell and we want to get something useful out of that, certainly, getting electrons out of our electrochemical cells is useful. But we also want to be able to extract work, work to do some kind of process, like maybe drive a car on batteries, right? So that will require work. And so to do that, we need to think about the units of our electrochemical cells, which for now we've used volts, right? Voltage. Well, as it turns out, a volt is by definition a joule per coulomb. So that is a joule divided by a coulomb. I can never spell coulomb. Sure, something like that. Okay. So joule divided by coulomb, where joule is a unit for energy, coulomb is a unit for charge. And so we can see just that. Our E cell potential, notice here I write negative work divided by Q. And it's negative work because that's work done by the system on the surroundings. So in other words, we make that work negative because we want our electrochemical cell to do work on the surroundings. Okay? And then that's divided by charge. So this just comes from our unit analysis. A joule is a unit for work, a coulomb is a unit for charge. And if I rearrange this algebraically to, calculate work, right? We just rearrange this and we get work equals negative Q times E cell. So we have a way of calculating standard cell potential. But what about calculating the charge? Well, as it turns out, the total charge delivered by our cell is going to be the number of moles of electrons transferred. And we'll do a sample problem here to see how we get that number. And this F is Faraday's constant. Okay, and so I'll speak a little bit more on where this Faraday's constant comes from, but for now we'll just treat it as a constant. Okay, 96,485 coulomb per mole of electron. And so you can see with the units here, this N is mole of electron, and this is coulomb per mole of electron. So the mole of electron and mole of electron cancels, and we'll have a coulomb times a volt. So a coulomb times a volt, which is the same thing as a coulomb times a joule per coulomb, and that just gives me joules that I need for work. Okay. So here's an example. So calculate the electrical work done by the following reaction. So I'll remind you, we did this reaction in the previous video. So this is the permanganate under acidic conditions, and we had to look these up in a standard table. And now here's where this is important, okay? For one, we have the cell potential, so that's what we need for this problem. Two, we have the number of moles of electrons transferred. So that's what that means. So on the manganese reduction reaction here, we can see it required 5 electrons. On the iron oxidation reaction, we had to bump that up by 5. And if you recall, we didn't change the standard potential, but as we shall see, that number 5 right here, 5 moles of electrons, that does tell us about how much work our cell can do, okay? So now we've already calculated that, and because we've already calculated the cell potential, will be a pretty straightforward calculation. Just kind of plug and chug in the formulas. So we know E cell is 0.74 volts. We know the number of moles of electrons was 5. So this formula is simply going to go work equals negative, I'll say 5 moles of electrons. And then times, let's see here, I lost my formula. Oh yes, I forgot to expand that. So work equals negative Q times E cell, and we know Q is N times F. So that's N times F times E cell, okay? So my Faraday's constant is 96,485 coulomb per mole of electron. And then my standard cell potential is 0.74 volts, which is the same as a joule per coulomb. I don't know if you can hear my cat meowing, but he's not happy with me right now. So I'm going to ignore him. So moles of electrons cancel, coulomb cancel, and we're left with joules. Okay, so let's carry out that calculation. So it's going to go 5 times the 0.74 times the 96,485, and that's going to give me joules. And I can see that that's negative 356,995 joules. And if I was using an appropriate number of sig figs, which for this, it'll just be 2 sig figs from my cell potential. And it'll probably be easier to express that in kilojoules. So that'll go 1, 2, 3. So that would be 357 kilojoules. And with only 2 significant digits, really, I should say that's negative 360 kilojoules. Okay, so if we construct a cell of this description, right, with the permanganate and iron half reactions, we'll get 360 kilojoules of energy out of that cell when we have 5 moles of electrons being transferred. Now, as soon as those 5 moles of electrons are transferred, it's done. That's how much energy we were able to release. Okay. So if we wanted to know like a total absolute amount based on a certain battery condition, we'd actually have to know the mass of that battery. And we're going to get to there eventually. Okay. So I want to just keep building on this and building this up for delta G. Okay, so an alternative name for Gibbs free energy is the maximum work function. And we kind of talked about this briefly, how Gibbs free energy kind of gives us like how much chemical work we can do. And if that's negative, if delta G is less than 0, we have work to give. Our system can work on the surroundings and it can do it spontaneously. So we remember that's spontaneous, okay? And if our delta G is greater than 0, we remember that's non-spontaneous. So in other words, the universe needs to provide some energy for us to carry that thing out, or we need to provide energy in that non-spontaneous process. So I could replace that simple formula that was work equals negative N times F times E cell with delta G equals negative N times F times E cell. And now we can see here why our voltaic cells are arranged to have maximum positive potential. Well, because if this number is positive, we've got a negative sign in the equation, so that means this will be less than 0. Thus, a positive cell potential gives us a spontaneous reaction. A negative cell potential gives us a non-spontaneous reaction, okay? And so here on Faraday's constant, I just wanted to talk a little bit more on where that comes from. So 96,485 coulomb per mole of electron. Well, as it turns out, if instead of thinking of this of charge per mole of electrons, what's the charge of one single electron? Okay, and so we can play with Avogadro's number there to see what that will be. So coulomb per mole of electron, and in 1 mole of electrons, there's, wrong number, 6.022 times 10 to the 23 electrons. And so if we carry that out here, so 96,485 divided by 6.022 e to the 23, and yup, there's the number. So 1.602 times 10 to the minus 19 coulomb is the charge of one single electron. So this is exactly what's giving us work in an electrochemical cell. every one of those electrons gives us 1.602 times 10 minus 19 Coulomb. A mole of those gives us 96,485 Coulomb, right? And we can see that as a principal factor determining how much work our cell can do, the charge of an electron, okay? And I think that I have one more problem here, yes, to work out. I will record this in a part B video.